Welcome to Shortcast, where we explore the fascinating world of science and technology in bit-sized podcasts. Today we're going to be talking about a subject that might seem simple at first glance, but is actually filled with complexities and nuances: the color of the sun. Most of us are familiar with the fact that the sun appears as a bright, white disk in the sky. But did you know that the sun actually emits light across all the visible colors in the electromagnetic spectrum fairly evenly? This means that when these colors come together united in sunlight, the sun appears white. In terms of classification, the sun is officially recognized as a yellow dwarf star or a G2V star, and it is at the upper end of this classification in terms of mass. When astronomers observe the sun, they do so across a range of wavelengths of light or electromagnetic radiation, including visible light and light not visible to the naked eye. Understanding the color of the sun is tied to our knowledge of the electromagnetic spectrum and these different wavelengths of light. The sun emits electromagnetic radiation across this spectrum except for gamma rays, which it does generate in its core. But these high-energy photons bounce around the dense interior of the sun, losing energy as they do so. This means when they finally escape the sun, they are longer wavelength, lower frequency, and lower energy photons. The quirks of the electromagnetic spectrum, energy, wavelengths, and frequency have a discernible effect on how we see the sun from Earth. When the sun is overhead, say at midday, and its light doesn't have to travel through much of Earth's atmosphere to reach the planet's surface, red, orange, and yellow photons reach our eyes mostly unaffected with little scattering. Thus, the sun looks white with a yellow, red, or orange tinge. But when the sun is on the horizon, such as at sunset, the situation is different, as its light has to travel further and through a denser region of Earth's atmosphere to reach the planet's surface. This results in blue light being more strongly scattered and thus mostly removed from the white light from the sun. This leaves mostly red light and makes the sun appear red. Similarly, dust particles and pollution in the air can also cause the sun to take on dull shades of red and yellow, or can even cause gray skies. However, these changes in the color of the sun as a result of these factors are superficial. The sun appears to have taken on a different color, but in reality, nothing has changed about its composition, structure, or function. When the sun does eventually change colors, it will be a result of much more significant transformations. In around 5 to 6 billion years, the sun will exhaust the hydrogen that it converts to helium at its core, as it comes to the end of its main sequence lifetime. When this 10 billion year or so balancing act ends, the core of the sun will begin to collapse, creating enough pressure to fuse helium in the core into heavier elements like carbon, nitrogen, and oxygen. The heat from the core will cause layers of the sun on top of the core to puff out, and hydrogen will begin fusing into helium in these layers. As the outer material of the sun expands outwards, the temperature of these layers will drop, and this will cause the energy of photons it emits to drop too. This means the expanding sun will take on a reddish-brown hue as it enters the aptly named red giant phase of its existence. Just as red often indicates danger in nature, this expansion and reddening of the sun represent the final risk for the Earth. The outer shell of the sun is predicted to expand out to around 100 times the star's main sequence diameter, completely burning everything in our solar system. But the future is still far away, and in the present, we're lucky to have missions like the Parker Solar Probe from NASA, which is designed to travel as close as 4 million miles.